Hey everyone, welcome back. In this example, we're asked to solve this polynomial inequality. We have the quantity x minus 4 multiplied by the quantity x plus 5 to the power of 3, which is also multiplied by the quantity x minus 1 to the power of 2 or squared. And we want to figure out when is the product of these quantities less than or equal to 0. And so we're going to discuss a method of solving this polynomial inequality entirely algebraically. But to help us get there and understand the procedure, we are going to mention or recall what we talked about graphing polynomial functions. And so solving our original polynomial inequality can then be rephrased, and it's equivalent to this question of when is our function f of x less than or equal to 0. And remember, f of x is like the output or the y value of our function. So really this is asking us, when does our polynomial function actually hit or is below the x-axis? Well, we could just graph our polynomial and look at the graph to help us figure out when exactly is our polynomial dipping below the x-axis or hitting it, because we can be equal to 0 here. But we can actually take out the whole graphical step and answer this question using a slightly different procedure, creating what we call a sign chart. And at this point, whether you create the graph of the polynomial or create one of these sign charts that we're going to in this example, it doesn't really matter. But knowing how to create a sign chart is going to be very, very important when it comes to working with rational functions later in this class, and also when working on certain types of problems in calculus. So just learning how to do the sign chart process here is what we really want to have as the takeaway. So what is a sign chart? We'll get it started over here. All a sign chart is a chart that tells us the sign of some quantity, and by sign we mean is it positive or negative. So on the bottom of our sign chart is just going to be a number line. We're going to label our x values. And on the top of our sign chart, we're going to label positive, negative, or 0, the sign of the quantity we are interested in. In this case, it's our function f of x, which we defined as that polynomial on the left-hand side of our inequality. And so the sign chart process is slightly different than our graphical process. The first thing we're going to look for are the zeros of our inequality or our polynomial involved. And because everything is written in this nice factored form, we know our zeros are going to be at x equals 4 from the first factor, x equals negative 5 from the second factor, and x equals positive 1 from the first factor. Now we can have the multiplicities help us for some of this analysis we're going to do, but we're going to see that it's not necessary because it'll be figured out through some other ways. So let's go ahead on our sign chart, label these important x values. On the far left we have negative 5, then 1 comes before 4. So the sign of our function f of x is not positive or negative at these x values. It's equal to 0. So that's what we're going to label on our sign chart here. And why we pay special attention to the zeros on a sign chart is because the functions we are working with are mostly going to be continuous or very few discontinuities we can include in the sign chart. We'll talk about that more with rational functions later. But basically, our polynomial here is a nice, smooth, continuous function. It doesn't jump all over the place. So the only way it can switch from being above the x-axis, positive, to below the x-axis or negative is by crossing through the x-axis or hitting one of these zeros. So these points at x equals negative 5, x equals 1, and x equals positive 4 are really the only locations where it's possible for our function to switch signs from positive to negative or from negative to positive. So we found all those potential sign switching spots. That breaks our number line into these 4 distinct intervals. And now we have to figure out on each of those intervals, is our function positive or negative? It has to be one of those two at this point. So how do we figure that out? Well, we just use test points. Nothing too fancy. Plug some numbers in and check out what happens. The kind of longer process is to sketch the graph of our polynomial and then look at the graph. But however, this test point procedure can be a little bit quicker. So when it comes down to picking our test points, we have to pick test points, which are going to be x values between our zeros or beyond our zeros for the far left and far right. So we need to pick some x value that is to the left of our furthest most left 0. And so our furthest left 0 is at x equals negative 5. Any number to the left of negative 5 will do. We want to pick a number that's easy to plug in, so let's go ahead and just pick negative 6. But if you wanted to, you could pick negative 5.0 0.00001 or negative 500 billion. They're going to accomplish the same thing. Next, we'll need a test point for these values between our next two zeros, between negative 5 and 1. Well, x equals 0 is between negative 5 and 1. I always try to use x equals 0 as one of my test points if I can. So our next interval is between 1 and 4. I think 2 or 3 would be excellent choices for that interval. For our last interval to the right of 4, let's go ahead and use x equals 5. So now we have to evaluate our quantity, x minus 4 times x plus 5 cubed times x minus 1 squared at these 4 distinct x values. All right, so I used a calculator to help us evaluate our function at these 4 test points. So when I plugged in negative 6 into the function, I got an output of positive 490. The part we care about more here is the fact that that is a positive number. So if we plugged in any x value to the left of negative 5, we'd always get these positive outputs. So we know our polynomial function is always greater than 0 when x is to the left of negative 5. So we don't want any of those x values in our solution set. Now we want to use the rest of our information to finish filling out our sign chart. F of 0 we evaluated to give us negative 500. So that means in this interval, the outputs of our function are always going to be negative. At x equals 1, we hit 0, so we could have a potential sign change, although we know what happens at these even multiplicities. We bounce off the 0, and no real sign change is going to occur. Our sign chart test points should verify this for us. We use our test point between 1 and 4, x equals 2. Plugging that into our function gave us this negative output of 686, but for creating the sign chart, we just care that it is negative. Our last output from our last test point was at x equals 5, and that output was positive 1600. So now that we have our sign chart completely filled out, we can use it to solve the original inequality in question. So when is our quantity less than or equal to 0? So we're equal to 0 here, here, and here, and we're less than 0 everywhere in between. So this interval from negative 5 to positive 4, including the endpoints because we can include the zeros, that interval is the solution to our polynomial inequality that we started with.